In physics, the concepts of work and power help us understand and explain lots of things in our universe. Let's start with work. Positive work is the energy we put into a system, and negative work is energy that's transferred out. Think of positive work as money being added to your bank account, and negative work as money taken out. In the metric system, work and energy are measured in joules. As an example, let's take a beautiful old mechanical grandfather clock. We transfer energy into the clock when we turn the crank to raise the heavy metal cylinders inside the clock. When we do this, we're doing positive work, adding energy to the clock. And that energy is stored as gravitational potential energy. We can calculate the amount of work done by multiplying the force we apply times the distance over which we apply the force. To raise the metal cylinders, we need to apply a force equal to their weight. That is, equal to the force of gravity pulling downward on the cylinders. These cylinders weigh 300 newtons, which is pretty heavy, about as much as a small child. And if we lift them 1/2 meter, then we do 300 newtons times 1/2 meter, or 150 joules of work. Power is the rate at which energy is transferred. When we say rate, we mean the amount of energy transferred per unit of time. In the metric system, power is measured in joules per second, or watts. The term watt goes back to James Watt, who came up with the concept of horsepower to measure the amount of power produced by a typical workhorse. James Watt was a producer of industrial steam engines, and he wanted his potential customers to be able to make comparisons between his steam engines and a familiar quantity, the power they could get from a working horse. This was such a useful idea that the metric system unit for power, the watt, is named after James Watt. Following in James Watt's footsteps, let's compare the amount of power it takes to run this grandfather clock to the power we'd need to run a bright 100-watt light bulb. We can measure the power a person uses to wind the clock by dividing the amount of work they did by the time it took them to do it. If it takes 1 minute or 60 seconds to lift the weights, then they are doing 150 joules divided by 60 seconds, or 2.5 joules per second of work. They're adding energy to the clock at a rate of 2.5 watts. You'd need about 40 times as much to run a bright 100-watt light bulb. Before we let the clock run, the energy is stored as gravitational potential energy of the cylinders. It's like your bank account when you have just deposited money. But if we let the clock run, the cylinders slowly move downward. Energy is leaving the clock. In fact, when the cylinders get to the bottom, all the energy that we put in will have left. So how much power does the clock use? That is, how many joules of energy per second leave the clock if it takes 5 days for the cylinders to return to their original position? We can figure this out because we already know how much work we did when we lifted the cylinders, 150 joules. But this time it took 5 days rather than a minute. 5 days is 5 times 24 times 60 times 60 again, or 432,000 seconds. So we divide the work done by the time and find an answer of about 0.00035 joules per second, or about 0.35 milliwatts. That's a tiny amount of power. This clock uses so little power that you could run almost 300,000 clocks using the same power it takes to run one 100-watt bulb. That's right, you could run a clock in every house in a medium-sized city with that much power. That's a pretty amazing conclusion, and it took knowledge of work and power to figure it out.